All right, welcome. Today we're going to peek under the hood of how pretty much all software works. We're pulling back the curtain on one of the most fundamental tools in all of computing, the compiler. It's really the unsung hero that turns our human ideas into digital reality, and we're about to find out exactly how. So, have you ever really thought about this? You sit down, you write some code, you hit run, and somehow it just works. Your computer knows exactly what to do. Now, it might feel like magic, but it's not. It's actually a fascinating process of translation, and that's the core problem we're going to unpack right now.
Okay, so here's the basic issue. We, as people, write code in what we call high-level languages. Python, Java, C++. They're designed to be readable and make sense to us. But computers, they live in a completely different world. They only understand machine code, which is basically just a long stream of ones and zeros. So how on earth do you bridge that gap?
Well, you bridge it with this: a compiler. A compiler is a special kind of program that acts like an expert translator. It takes the code you wrote, the source language, and it meticulously converts it into the target language that the computer's processor can actually understand and execute. It's the absolute crucial link in the chain.
So this graphic really lays it out. On the left, you've got your source code. That's your idea, written in a language that makes sense to you. In the middle, the compiler works its magic. And then, out the other side comes the machine code. Those are the raw instructions the hardware can actually follow. It's a simple idea, but trust me, it's incredibly complex in practice. Now, the second you decide you need to translate something, you run into a choice, right? Do you translate an entire book all at once, before anyone reads it? Or do you do it line by line, like a live interpreter at a conference? This exact choice leads to two very different paths in programming. And this table just lays that choice out perfectly. On the left, you've got the compiler. That's our translate the whole book approach. It scans the entire program at once and creates this optimized final version, which means execution is super fast. On the right, you've got the interpreter. It's our live translator. It reads and runs your code one line at a time. Now, this is slower overall, but it is fantastic for debugging because it stops the very second it finds an error. And that's why languages like C++ use compilers for raw performance, while languages like Python and Ruby often use interpreters for their flexibility.
But of course, the story doesn't stop there. As software got more and more ambitious, just choosing between fast or flexible wasn't really enough. New, more complex problems popped up, and they required new, really clever solutions. And that meant entirely new types of compilers.
And here's the first really big one. What if you want it all? What if you want that lightning-fast execution speed you get from compilation, but you don't want to give up the dynamic, on-the-fly nature of an interpreter? Is there any way to get the best of both worlds?
Well, yes, there is, and it's called just-in-time compilation, or JIT for short. Now, unlike the traditional approach where you compile everything beforehand, a JIT compiler is this awesome hybrid. It actually starts out by interpreting the code, but it's also watching. It's looking for the parts of the code that run over and over again, what we call the hot code. And then it compiles only those sections into super fast machine code right in the middle of the program running. It's a brilliant way to get a performance boost exactly where you need it most. Okay, here's another challenge you see all the time. Imagine you're a developer. You're building an app for an iPhone, or maybe a game for a PlayStation. The thing is, the processor in your computer is completely different from the one in those devices. So how do you write a program that will run on hardware you don't even have?
The answer is a cross-compiler. This tool is amazing. It runs on your machine, but it targets a different one. It knows the specific architecture of, say, a smartphone or a gaming console, and it produces the perfect machine code just for that system. Cross-compilers are really the backbone of modern software, letting developers build for billions of different devices all from a single computer.
Now for our last problem, which is a bit more subtle. Technology moves incredibly fast, right? A programming language that was cutting edge 5 years ago might be kind of outdated today. So what do you do when you have a massive old code base? How do you upgrade it to a new language? Or how do you get two similar but slightly different languages to talk to each other?
For that, you use a source-to-source compiler, but everybody just calls it a transpiler. Now, instead of going from a high-level language down to low-level machine code, a transpiler translates from one high-level language to another high-level language. It's less like translating a book into binary and more like translating modern English into, say, Shakespearean English.
And these are used everywhere.
A really famous one is Babel, which takes modern, fancy JavaScript and converts it into older versions that can run in basically any web browser. Or there's Swiftify, which helps developers upgrade their old Objective-C code into Apple's newer Swift language. These tools are absolutely essential for keeping software modern in our constantly changing digital world.
So after all that tech talk, why does any of this matter to you? Well, because these silent translators are working behind the scenes in almost every single piece of technology you use every single day. They would make things fast, powerful, and accessible.
So what are the big things to remember? First, compilers are the essential translators that power our software. It's that simple. Second, that choice between a compiler and an interpreter, that's a really fundamental trade-off between speed and flexibility. And finally, all these specialized tools like JIT compilers and transpilers, they didn't just appear out of nowhere. They evolved to solve very specific, complex problems, which gave us this powerful idea of compile once, run everywhere.
And this quote just hits the nail on the head. Grasping what compilers do is really the key to understanding how we build the efficient, reliable software that our entire modern world depends on. It's the difference between just using technology and truly understanding how it works. Which brings us to one final thought. We've seen how compilers have evolved to solve the problems of their time. So, what's next? As technology keeps racing forward, what new problems will the next generation of compilers need to solve? Will they be translating our thoughts directly into code for AI? Will they need to optimize programs for quantum computers? The next set of challenges is already out there, just waiting for the next generation of these brilliant translators to come along and solve them. Thanks for tuning in.